So here's a retake of the video where I do some of the calculations for the first chunk of the electricity chapter. We're going to go through several calculations, and I have corrected the one that gave us some trouble the first time. First thing, what you're going to do when you're watching these videos, as usual, is you're going to pause the video right now and see if you can solve this problem yourself using the 7-step method. So press pause now and give it a try. Okay, 7-step method. Step 1, what is it asking for? What quantity of charge? That would be Q equals something, and it's going to be in coulombs. And if we look at this, we've got 3 sig digs here and 3 sig digs here, so the answer is going to have 3 sig digs. Step 2 is to draw a picture. Well, we've got a person, and we have a doorknob, a very big doorknob because I have trouble drawing small ones, and we have a shock going in between. So I'm asking how much charge is being transferred. Step 3, given information, we have a potential difference or voltage of 250 volts, and we have an energy of 12.0 joules. Formula, that's the next step. We're looking for Q, so we need something that starts with Q, but we may need to rearrange one. So let's look at what we know. A formula that involves potential difference, energy, and charge is that the potential energy is equal to energy over charge. The potential difference, sorry. If we rearrange this for Q, we take the Q up to the top, we take the V down to the bottom, and we're left with Q equals E over V. So now we have done our step 4 and our algebra in step 5. Plug numbers in, and we're going to get an energy of 12.0 over 250. So that's joules over volts. Now, a quick little mental math thing on the side here. Let's do this mentally. The easiest way to do this would be to say we are talking about something in the range of, well, 1/10 of 250 is 25. 1/10 of that is 2.5. So 1/100th of 250, or 1% of 250. Another way, 0.01 times 250 is 2.5. Now 2.5 times 4 equals 10. So that's going to give us 0.04 because we did 4 of 1%. And then what we have left is 2. So 2 over 2.5 is 0.8, which is going to translate to 0.8 times 0.01. So 0.008. So the answer is going to be 0.048, and it's coulombs. You can plug that into your calculator if you're not interested in the mental math. That's fine. You should have, ideally, paused at this point. The 2 spots that you pause at for sure are there, and there. And honestly, pause at any point where you didn't do what I do. Okay? So question 2, the next question in this series, is using the second equation that I taught you. We have a light bulb. So light bulbs, the inside of the light bulb looks like this. It has a little coil. And I'm saying in one point, how long does it take for a certain amount of charge to pass through it given a current? So step 1, I'm asking for time. Remember, you should have paused at the beginning. Pause now. See if you can solve the rest of it. There's step 1, step 2. Step 3, given information, current equals 0.835 amps, and charge, the amount of charge that's going through is 1.35 coulombs. An equation, a formula, ideally that uses these 3. Well, we know that current is equal to Q over T, the amount of charge passing in a given amount of time. we need to rearrange this for time. And again, it's the same kind of rearrangement as the last one. Time gets multiplied, so it ends up on top, and current gets divided, so it ends up at the bottom. Then we get Q over I. Step 6, plug in the numbers. Q is 1.35 coulombs, and current is 0.835 amps. And when we multiply that through, or put those numbers through, do your own calculation here, make sure you're good on the calculator, 1.6167 something. We only need 3 significant digits. I get that because that's 3 and that's 3. So 3 significant digits here is going to be 1.62 seconds. Next one. See if we can get all of these in 10 minutes. So I taught you Ohm's law. This is a throwback to grade 9, so try it right now as it is. Okay, so your target, we're asking for the current. I equals something amps. That's right here. What is the current? Step 2, draw a picture. Well, we don't really have to draw a picture for this, but yeah, we have a current going through and a potential difference, no, a resistance of the toaster, and we're asking for V equals what? That's a potential difference across that resistor. Okay, the toaster is essentially a resistor. So, step 3, given information, resistance equals 84.5 ohms, and the voltage or potential difference is 120 volts. Step 4, find a formula. We know that it's Ohm's law, and we probably know Ohm's law in terms of current. It's going to be this potential difference divided by the resistance. Plug numbers in, 120 volts divided by 84.5 ohms, and our current comes out to 1.42 amps. Remember to pause. Try that again in the next one. So now we're looking at cost. Now I didn't give you a formula for cost, but I did ask you to look at the numbers. I will give you the formula now. It's not really so much a formula as understanding the units that we're dealing with here. So first, you try and see if you can figure this out yourself. Pause the video. Once you've done that, let's take a look at it. What is the cost? So I'm just going to write the word cost, and it's going to be something dollars, presumably, because we're given the number in dollars. We might as well use dollars as our final unit. That's one less conversion to do. The diagram, well, you could maybe do a timeline for this, right? We have the month of February, and it's running for that time. We've got a certain power running for that time. And we have a cost per kilowatt hour. So there's a few ways you could draw that. I don't really have any comfortable ways to do it for me, so I don't draw a picture unless I discover later on that I need one. Now, what do we have for given information? We have power equals 250 watts, which is 2 sig digs, by the way, which means, yeah, this is 2 sig digs, so that should be a 2. Power, and we have the cost. Let's do it like this. The cost per unit. I'm going to use the cent symbol because we don't use it for anything else. And that's going to be $0.095 per kilowatt hour. Okay, so this is where we get our formula. This is how we start to work out our formula. This is a little bit of a challenging question because I'm expecting you to work out the formula if you don't already know it or haven't looked it up. So here's what we're going to do. We're going to say we have to cancel out kilowatts, we have to cancel out hours, which means we have to put something on the top that's power and something on the top that's time. And that kind of makes sense because kilowatt hours is a measure of energy, which is power times time. So let's take a look at how this works. If we say that the cost is equal to the power, which is P right up here, times the time, times the cost, let's just check our units on this and make sure that it's working. We're going to have watts times presumably hours, we can work that out in hours, times the cost, or dollars per kilowatt hour. And if you look at that, you can see with some conversions, you should be able to cancel things out and leave yourself with the dollars. So this should work. And if you check this in the textbook, this is the formula that we use for it. So let's put the numbers in. We are looking for cost, so we don't need to do any algebra here. Put the numbers in. We have 250 watts. You'll see now why it's often a good idea to put the units in. Time is going to be 24 hours times 24 hours per day, yeah, 24 hours per day times 28 days in a month times 1 month. That's our time, because it's 1 month, it's a month of February. And then we're going to put our cost in, which is $0.095 per kilowatt hour. And we have one more thing we have to toss in here. I'll put it in red because it's not immediately obvious, and that's that we have kilowatts on the bottom and watts on the top, so we have to switch that up. And the way we do that, we do something that's got kilowatts on the top and watts on the bottom. 1 kilowatt per 1,000 watts. Okay? Now you could have just converted this immediately into kilowatts if you wanted. That would also work. Here we go. Plug the numbers in. Let's do the cancellations first. I'll do it in green because that changes all the colors. Watts is canceled by kilowatts way down here. Hours is canceled right here. Days is canceled right beside. Months is canceled there. And we have kilowatts on the bottom, kilowatts on the top, and we're left with dollars. So we're going to have 250 times 24 times 28 times 0.095 all over 1,000. And the symbol is going to be dollars. When we plug that number in, we get 15.96. So we've run that refrigerator for a month completely, never stopping. It comes out to 15.96. And of course, SigGauge will turn that into $16. All right, last one, 12 minutes. I'm just going to ask you to pause this and read it once I finish speaking. But we talked about power today, which is this one. The power in a circuit, power being transmitted. That's what this stands for. Transmitted power is this value, the volt potential difference across the transmission times the current being transmitted. And what I'm asking you to do is try a little bit of algebra. We'll come back to this next week. But try a little bit of algebra and see if you can work out power lost to a resistor as a function of, let's make that a capital S so it's clear that it's a function. No, small f is right. V, R, and V. And power loss as a function of R and I. Give it a try. Meanwhile, you can practice some of the other stuff in Chapter 11, and within the next day or so, we will be starting into circuits. Good luck. See you tomorrow.